Hi class, we continue our study in chapter 3 talking about parallel and perpendicular lines by moving into section 3.4. And section 3.4 is about proving theorems about parallel and perpendicular lines. And the good news is this section is actually pretty straightforward and won't take too long to go through. So we have two objectives. The first is we want to use and prove theorems about parallel and perpendicular lines. And then we want to use algebra to find measures of angles related to perpendicular lines. All right, so I want to start with two postulates that we had from previous sections. All right, so we had this one, the parallel postulate, and it says through a point not on a line, there is one and only one line parallel to the given line. So if I have this point hanging out here in space and I have this line L, well then guess what? There's only one line that goes through point P that is also happens to be parallel to line L. We have the perpendicular postulate. Through a point not on a line, like point P here, not on a line, there is one and only one line perpendicular to a given line. So if I have this line L, and I have this point P hanging out in space, there's only one line that goes through it, that's perpendicular. Remember, perpendicular lines form 90-degree angles. Okay. All right, so we have this perpendicular transversal theorem. So theorem, in a plane, let two parallel lines be cut by a transversal. So we have these two parallel lines, L and M. You can tell they're parallel by this notation here. If a transversal is perpendicular to one of those lines, like line L, then it is perpendicular to the other line, like line M as well. All right, so now forgive this is a typo that's not coming up in the slides, but so whenever you see this, know that if L is parallel to M, that's what it's missing the double lines there, but if L is parallel to M and T is perpendicular to L, then it must be the case that T is also perpendicular to N, right? If L and M are parallel, and we have this transversal that cuts it, so it's perpendicular with L, also got to be perpendicular with M. Another one, if two lines are parallel to a third line, right? Theorem 3.4-2. So if two lines are parallel to the same line, then all three are parallel to each other. So remember, if the typo here, if A is parallel to B and B is parallel to C, well then also it must be that A is parallel to C. All right, let's talk about how you would prove the first theorem I talked about, theorem 3.4-1. All right, so in a plane, if we have L is parallel to M and T is perpendicular to L, how can we prove that T, this transversal, is also perpendicular to M? All right, so we're going to do a two-column proof for this. All right, so let's start with our given statements. L is parallel to M and T is perpendicular to L. That's given. Well, we know that angle 1 must be congruent or equal to angle 2. All right, why do we know that? That's just the corresponding angles converse. Next, we know that angle 2 is a right angle, right? That's by the definition of right angles, obviously. And then by extension, it has to be a result that T is perpendicular to M because we know that 2 is a right angle, and that's by the definition of perpendicular angles. So that one was an easy one to prove. All right, let's talk about theorems about perpendicular lines. This is theorem 3.4-3. If two lines are perpendicular, then they intersect to form four right angles. That makes sense. So if we look over here, if we have L is perpendicular to T, then it must be that measure of angle 1 is equal to measure of angle 2 is equal to measure of angle 3 is equal to measure of angle 4, which indeed are all 90-degree angles. Another one, all right, this is theorem 3.4-4. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular to each other. So if we have a linear pair here, all right, like line L and M here, angle 1 is equal to angle 2 and form a linear pair, right? So if these two angles are equal to each other, then it must be the case that they're both right angles, right? Because this line M is a flat line, and it must be that L is perpendicular to M. Let's do an example real quick. All right, let's find the value of X here, all right? Now, if you look here, I have this line L and this line N here, and what they're telling me here is that angle 1 here is a 90-degree angle, right? What that also tells me is this part here has to be 90 degrees. The sum of these two angles have to be 90 degrees, and the sum of these two angles have to be 90 degrees. So the measure of angle 1 is 90 degrees. We see that n is perpendicular to L. So if n is perpendicular to L, then all angles formed by these lines are right angles. Great. So we have 63 plus x has to equal 90 degrees. Subtract the 63 over, and x just has to be 27 degrees.